Welcome, everybody. You're joining us now for Freeform Optics for Imaging Mid-Spatial Frequency Errors. This webinar is part 3 of the 2021 Freeform Optics series, and today's session is sponsored by Lambda Research Corporation and hosted by Photonics Media. I'm Sarah Weiler. I'm the webinar coordinator at Photonics Media. So this is an exciting 3-part series, as many of you probably know, but in case you missed parts 1 or 2 or want to go back and revisit them, these were the topics for each one. So in part 1, we heard about design methods from Dr. Janique Roland and Dr. Aaron Bauer of the University of Rochester. In part 2, we heard about manufacturing methods from Dr. Matthew Davies of the University of North Carolina at Charlotte and from Dr. John Lambropoulos of the University of Rochester. And finally, in part 3, today we're going to be hearing the final presentation in this series from Dr. Tom Selewski of UNC Charlotte on mid-spatial frequency errors in freeform optics. You can watch all of these webinars on the Photonics Media website for free. Today's event is going to be available within a few days. And if you have any technical errors during the show, don't worry. You can try logging out and coming back in, but if it doesn't fix it, you will be able to access the recording very soon. And if you have any questions or comments during the show, we encourage you to write them into the chat at any time, and we will get back to you either during the live Q&A today or after the event by email. And you can download the paper behind this series, Freeform Optics for Imaging, directly in the webinar chat. I've got a link in there for you, or you can search on your web browser for Optica Freeform, and the paper will come right up. So to give you a little bit of more background on Dr. Tom Selewski, he is a professor of physics and optical science at the University of North Carolina at Charlotte and site director of the National Science Foundation Center for Freeform Optics, or CFO, which is at UNC Charlotte. He has over 25 years of experience in optical design and manufacturing and worked previously at Digital Optics Corp on the design, application, and manufacture of micro-optical components and systems with military and commercial partners. He is co-author of Diffractive Optics, Design, Fabrication, and Test, and serves as senior editor for the SPIE, Journal of Optical Microsystems. He's the 2017 recipient of the John J. Turin Award for Outstanding Career Accomplishments from the University of Toledo and is a fellow of OSA and SPIE. So that's all from me. I would like to welcome Dr. Tom Selewski.
All right. Thanks very much, Sarah. I really appreciate the kind introduction. Welcome the opportunity to speak to the audience today. As Sarah mentioned, this is the third talk in a series about freeform optics, so I'm not going to spend a great deal of time talking about the broader area, but I did want to do a couple of quick reminders. When we talk about freeform, again, we're talking about sort of new paradigms in optical design where centuries of systems and components based on radial symmetry are being replaced with things without axes of symmetry. Okay, there's been a number of advances that have been developed, particularly in recent years, that have really enabled this sort of leap forward. Advances in computer-aided design, advances in computer-controlled manufacturing and measurement and metrology. And these things, and again, these were talked about in quite a bit of detail in the earlier talks in this series. But these advances are enabling improved performance, reduced size and weight, reduced cost, and elimination of assembly steps. Okay. Now, in the context of today's discussion, I'm going to talk about sort of a byproduct, or if you will, a consequence of the techniques that are used to make freeform. So specifically, the subaperture manufacturing methods that are required to make freeforms can leave residual surface errors, okay? And these surface errors can present challenges, and that's really going to be the focus of today's discussion. Now, as Sarah mentioned, this work, a majority of the work that I'm going to talk to you today was part of work we've been doing through the Center of Freeform Optics. Sort of had the privilege to have been affiliated with CFO since its inception in 2013. And we've had a strong collaboration over this time with a wide variety of industrial affiliates and members of this center. So I really want to thank all the members for their support and involvement in all this work. And again, there's more information available about CFO on the website as shown here. Now, and Sarah also mentioned, the handout for today, if you will, the recent paper from Optica on freeform optics for imaging. I'm going to sort of point you to this paper. There's going to be a number of references that I'll provide kind of in context during the discussion today. These references in general are included in this Optica paper, so I'll point you to that paper for wanting to dive into a little more detail on any particular topic. Okay. All right. So now with this, again, the focus of today's discussion is mid-spatial frequency errors. And as I alluded to before, these are byproducts of the manufacturing methods that are used to make freeforms. Okay. They go by different names depending on maybe who you're talking to or in different contexts. So you'll see it written maybe mid-spatial frequency or just MSF for shorthand errors. Sometimes it might be referred to as ripple. In some cases, it's referred to as waviness. But in the context of our discussion today, we're talking all about the same thing. The different subaperture processes that can be implemented to make freeforms, and I mentioned these processes can apply to radially symmetric components as well. But processes like diamond turning, diamond milling, grinding and polishing, magnetorheological finishing, and so on, are all going to have different characteristic, what I'll refer to as a signature, this residual texture that's left on a surface. Diamond turning will tend to have more of a spiral type or pattern. Diamond milling, more of a linear raster pattern, and these can apply to grinding and polishing as well, depending on the tool paths that are used. More conventional polishing might have sort of random or rotational tool, so this can result in like a spoke-like pattern. I'll show some examples of that here in a little while. But when we talk about this in the context of mid-spatial frequencies or MSF errors, thinking about where do they come from? They're these undesired byproducts of the manufacturing processes. What are the sources? I would say kind of maybe one of the main sources are the tool paths. I mentioned about spiral turning or raster milling or so on. So these characteristic tool paths can leave characteristic textures. Okay, but there are other sources of errors as well. Alignment of the subaperture tool maybe to a motion axis or rotation axis, vibrations in the systems, thermal variation, expansion and contraction of the parts or the machinery during manufacturing, the abrasive wear or chemical wear of a tool, maybe even a diamond tool or a grinding wheel used during manufacturing, the material properties themselves, and so on. So lots of potential different sources for the errors. And when we consider all these and we think about, well, how can these add up and show up in a pattern? They can end up being fairly involved, fairly complex. So there's a couple of representative examples that I've shown here through simulation, just sort of trying to get a visual picture of what do things look like. So imagine I've got a shallow lens, and in the top example here, I'm assuming diamond turning. So I've got a sharp diamond tool that I'm using to sort of basically cut away a section of the material. So I'll get what I call a cusp-like shape from the radial shape of this very small tool. There can be thermal variation or thermal drift between the diamond tool and the part being machined during the process. That I'm showing here approximated as a sinusoidal lower frequency error. But all of these things combine and leave me with, now I've made a lens, I've got the nominal base curvature that I've shown here that I want, but I've got this residual, maybe more complex texture on top. Similar idea here, if I was to make this same nominal structure, but through raster milling, I've got my cusps, I've got my thermal drift, but rather than having radial symmetry, it's more just in one direction. So I get a more a system that looks a little, quite a bit different from the error that I got from the diamond turning. Okay, so sorry here, a little stuff. So those were a number of synthetically generated app errors, just created mathematically in a modeling package. Here are some examples of some more complex errors. that can occur. So this is sort of a rogues gallery, if you will, of experimental surface error maps, nominally mid-spatial, after filtering out of different frequencies. And you can kind of see there can be a lot going on here. You'll see some where they're nominally radial symmetry in the pattern, some where you see more linear or raster type patterns. There are some where the patterns you're seeing in this one are more characteristic of the spoke-like patterns that I mentioned. And then combinations. This is a particular interesting one here, where you've got both a radial and a linear raster pattern in the same thing. So again, quite complex errors that can come about. Now, when we talk about mid-spatial frequency errors, I mean, we're using the term, but haven't really defined in any formal way what they really are yet. As you might guess by the name, spatial frequency and mid, sort of there's a range there. If we think about the types of errors that generally you might find in I'll just say generically a lens, we tend to think about form errors or figure errors. These are the more conventional sources of aberration that we might find in a system. So on this power spectral density or PSD plot, which again is just sort of showing a measure of the amplitude of the errors on a surface as a function of the relative length scale, or the inverse in this case, the spatial frequency. The low frequency errors or figure errors are at one end, and then sort of an area that I'll loosely refer to as finish, or otherwise sometimes known as roughness, higher frequency sources of error. And then there's this middle ground, okay, the mid-spatial regime. Now, if we think about what these different frequency ranges do, what are the impacts of these on performance? Speaking in sort of broad terms, mid-spatial frequency errors are going to change the energy distribution in the system. So depending on the frequency, it's going to depend where does the energy go. So if I think about low frequency errors, these are the kinds of errors we tend to think about as conventional aberrations that are going to change the shape of the point spread function or your imaging spot. A high frequency or roughness is going to tend to direct or scatter light, generally at much higher angles, tend to end up having sort of a more low, the energy comes out of the main peak, but sort of a lower, wider spread distribution of background noise, decreasing your signal to noise ratio and so on. And then mid-spatial is sort of in between. So in this work here shown from James Harvey, this is sort of assuming that the errors are nominally statistically spread out. I'm going to get what he referred to as small angle scatter. So I'm directing light out of the main point spread function, but it's still pretty close. So it can end up having a fairly significant impact on the performance of the system. And we're going to talk quite a bit more about that as we go through the discussion today. Okay. So you'll notice when I talked about, I said there's low frequency and high frequency and mid frequency, but I never really defined where the lines were. So there's a question when you see an error, is it a mid-spatial? And the answer to that question can be maybe a little confusing, or it can depend on who you're talking to. It can depend on the paper you're reading. But there's a couple of some general ideas that we want to make use of. Sort of one fairly specific definition. So this is some work by Dave Akins and Jessica Green and Richard Youngworth. Proposed defining what the lower end of the mid-spatial regime as being defined by subtracting the fit from a Zernike polynomial expansion, so the first 37 terms. That's going to define where the low end comes out, and then define the high end based off of the Fresnel length of the system and the distance to the image plane. Okay. So that's a fairly technical and definitely something, it's wavelength dependent. It's dependent on the length scale of the errors in the surface and so on. So ISO 10110-8 is the sort of the relevant standard for optical drawing. And you talk about defining waviness, which is are basically the mid-spatial frequency errors we're talking about here. It allows user definition of the range of mid-spatials, but if you don't define a specific range, there's a default range from 80 microns at the low or the higher frequency and the shorter period, or up to 2.5 millimeters. Now, visually, you can kind of see what do these look like here. Again, from the Akins paper, kind of filtering out a more complex surface, low spatial frequency errors, and high frequency roughness, and then sort of this mid-spatial regime, this different, more complex texture. Okay. The thing that is maybe the takeaway of this is to remember that the spatial scales for mid-spatial frequency errors are functionally dependent on the operating wavelength. I mean, I could have a particular residual surface error from a process that if I'm using if this component is something that I made for operation in the infrared, I might be able to treat it as a roughness and maybe the impacts are not so big. But if I had that same texture, but then was trying to use this part, maybe it was also intended to be work in the visible or in the ultraviolet, then it's going to be a much bigger problem. It's going to fall more into this mid-spatial regime that could cause me maybe unanticipated problems and issues. Okay, so a little bit of a historical purview, or I guess review, kind of going through this talk. Looking at this idea of sub-aperture manufacturing, early studies on what are the impacts of these residual errors. I'll make some generalizations here, but they tend to be primarily statistical in nature. Assuming sort of isotropic or random distributions of error, and then any structured errors that were assumed to be pretty smaller in comparison to the random work. So, some of the earlier work, just looking at roughness characterizations from diamond machining, from Church and Zavada and Stover, for example, actually used extensions to perturbations to Rayleigh-Rice scattering theory to understand what's going on in here. Sort of maybe one of the first sort of actual identifications of this range called mid-spatial, some work from Knoll in the late 70s, and then from Mirage and Slansky in the early 80s. Very, very important work from Harvey and Kotha in the mid-90s, talking about, again, just general scattering effects from residual optical fabrication errors, looking from, again, sort of figure, mid-spatial, and roughness kind of all together, and looking at the relative impacts of each. And then a particular example that I'm going to spend a little bit more time on is some work by Youngworth and Stone in 2000, where they developed a way to estimate the impacts. So, not just describing the surface, but can I predict from the error in the surface what impact it's going to have on optical performance? Okay. I'm going to spend a little bit more time talking about this particular paper. So the assumptions that were made here, again, assuming random distributions of the errors themselves, sort of near normal incidence in the light hitting the surfaces, and using the idea of perturbation theory. So the mid-spatial frequency errors are assumed to be small, and they're treated as perturbations, that sum up in the wavefront of the summations of the wavefront in the exit pupil. Okay, so a lot of detailed mathematics and analysis, but a fairly simple results that come out the other end, where they're able to, based off of just knowledge about the refractive indices of the materials and the surrounding media, the band limited root mean square RMS error for H surface, able to predict with pretty good accuracy, as I'm going to show, what's the impacts were, what was the resulting Strehl ratio in the system, and what's the resulting modulation transfer function, or MTF. Okay. So, and one of the things I'll point out here is that with this calculation, it can actually predict sort of a good estimate of the modulation transfer function, and it's really just multiplying the nominal modulation transfer function times the Strehl ratio predicted by by the mid-spatial frequency errors. Okay, so let me show that in a little more visual form. So this is an example from this paper. So the nominal pattern assumed it was an IR objective lens. So it's 5 different lenses, 10 different surfaces in this system. and then they assumed 3 different mid-spatial frequency signatures or patterns. So these two are more, I'll say, spoke-like, more from polishing. Here's one with more of a radial symmetry. And they assumed that these 3 different errors were distributed in what I'll call a pseudo-random manner across the 10 different surfaces. So one on each surface, but in just sort of different configurations. Looking at the numbers here, for this particular example, again, it's infrared, so the assumed wavelength is 3.7 microns. And then the RMS wavefront error of this for each individual surface was, in the example shown here, a 200th of a wave, so a fairly small amount. But again, remember, this is on each of the surfaces. So if we use the equations that they came up with that I showed on the previous slide and say, well, what impact, what will this do to the MTF of the system? We can look and see and predict what happens here. So this is showing the on-axis MTF for a couple of different assumed RMS error distributions. So for the case here with 200th of a wave, I look at what I have over here. So I've got my ideal MTF right here as a, so modulation is a function of frequency. So that ideal means assuming no mid-spatial frequency errors. Now, if I assume that I have my 200th of a wave RMS error on each surface, do my calculations, I predict a effective Strehl ratio of 0.9, and then I always said, well, I can just multiply the ideal MTF by my Strehl ratio, and I end up with an approximation to the real MTF. So you'll see a set of dashed lines right here with a solid line on top. So the solid line is the more rigorous model. The dashed line is the prediction from this estimate that I showed on the previous slide. Now, assuming that the RMS error on each surface is a little bit higher, so if this 3, rather than a 200th of a wave, it's 3/200ths of a wave. The predicted Strehl ratio drops from 0.9 to 0.57. And then the same idea, we look and we see this predicted estimate of the MTF from that simple calculation. And it actually matches quite well with the more rigorous calculation. So this is a very important, this is a very useful method for understanding what are the impacts of the RMS. What does it really do to the performance of my system? Okay. So moving forward now, I want to point out an additional body of work by John Tamkin and others in 2010. So there were 3 key papers that were published that explored the impacts of what I'll refer to as structured mid-spatial frequency errors on performance. So the previous work that I've been alluding to and talking about, again, it used statistical methods or small signal approximations to describe the impacts. So the work that Tamkin and the group did addressed this by, and I'll give this in quotes, by acknowledging that these errors cause grating-like image artifacts. It's spatial frequency, the frequency, it implies periodicity, very much in line tied to gratings, right? So these grating-like image artifacts are going to have appearances and magnitudes that cannot be predicted from statistical approximations. Okay, so a couple key observations from this, the idea that if I've got a single frequency surface ripple, maybe described as a sinusoid, it's going to yield multiple order diffraction spots in the image plane. Makes sense. The amount of energy in those spots, or the diffraction efficiency, is going to be nonlinear with the phase or with the surface height. And more complex surface height errors can be represented by a harmonic decomposition of sinusoids. So I mentioned like the cusp-like errors before. Those are obviously not sinusoids, but they could be described as a harmonic summation of sinusoids. So some of the consequences of this, and I'm not going to go through all of them, but just sort of some key ones to take away. Generation of ghost-like images from the diffraction orders, and then field dependence of the image artifacts. So again, these are things that are not really described or predicted by the statistical methods. So thinking about this, for example, the idea of field dependence. If I look at a particular surface, so let's assume I've got a diamond turned structured surface here. And I think about light coming from different field angles, and depending on where it hits this particular surface, it's going to change the impact. The diffraction pattern, if you will, generated by hitting that is going to change. If it's the center, I've got this radial symmetry. I'm going to get a radially symmetric point spread function. If a small window hits near the edge of the surface, it looks more like a raster pattern. So I'm going to get what we might assume as a more conventional diffraction grading like pattern. So this is going to impact the performance. Obviously, this is showing the modulation transfer function at different field angles. And when we talk about representing the data, how do we measure the data and capture this? Sort of, revisiting the power spectral density plot I showed earlier. So the earlier work was sort of assuming a random distribution. When I've got these structured errors, I'm going to get spikes, periodic structures in my distribution that are resulting from the manufacturing process. Okay, so now building on this, we talk about modeling and ultimately tolerancing of these, what could be more complex errors. We think about how do we represent the errors. Maybe the simplest way conceptually is just a point cloud of data. More involved, it might involve a decomposition into a set of orthogonal polynomials. I'll talk about pros and cons of both of these in a minute. But fundamentally, when we talk about this, these mid-spatial frequency errors, again, following the idea from Tamkin, they're modeled as conformal diffraction gratings or phase screens that are superimposed on the underlying component. Okay. As we said before, they're periodic. The dimensionality means we really need to, ray tracing is really not the way to go. We really need to think about wave optics or physical optics models. And then depending on the method that I use, again, I could use the point cloud, maybe get very high resolution, but it can give me a very large data set, which for a physical optics model might be very intensive on the computation side. I might be able to decompose this into a different basis set, which might facilitate some of the later analyses that I want to do, but I might need a lot of terms. Okay, I want to talk about the decomposition in a little more detail, just some of the work that's been done. I mentioned the work that Tamkin did to basically just a Fourier series decomposition. There's been, I'll say much more involved or more advanced work that's been done that's built on that idea. So a lot of work done by Greg Forbes on gradient orthonormal polynomials, or what are conventionally now known as Forbes polynomials or 2DQs, or there's other names that are used. Zernike polynomial representations using radial basis functions. More recently, some work on what are known as rapidly decaying Fourier-like bases. And all these I've provided the references here. All these different methods have been used and demonstrated to have some useful properties when we think about better understanding and modeling of mid-spatial frequency errors. Okay. Now, one particular example, a conceptual example, talking about this idea of, what are the benefits of maybe decomposing what could be a complex error. So consider this example right here. This is a fairly complex error map from a pattern, and we look at that and we say, well, okay, what does it do and where did the errors come from? And it might be challenging to figure that out just by looking at this. But here's an example. If I were to take this and decompose this into a Zernike polynomial basis set. So again, a weighted summation of what could be a very large number of Zernike polynomials. I'm showing basically a map of the coefficients here as a function of the orders m and n of these parts here. This decomposition allows us to look at different, what I'll refer to as different bands, different spaces within the pattern. So in this particular case here, m0 through m equals 8, I filter out, I get a nominally radially symmetric pattern that I can treat and look at separately. In this range here, I've got my more spoke-like pattern. So I can look at these different ranges, these different bands, and look at what are the impacts on performance of each individually. But I can also use this maybe as a way to identify what are the sources of the errors in the first place. I mentioned, the spokes tend to be more related to a polishing pattern or orbital polishing and so on. So I'm not going to go into any more detail, but I just want to point out this decomposition can be quite helpful. Okay. Now, building forward on the idea of modeling, some additional advances. Again, this is not a complete listing, but just better understanding of modeling and of mid-spatials in optical systems. Again, building on from the earlier work, statistical, then the structured work from Tamkin. So a large body of work from Miguel Alonso and Greg Forbes and Kevin Lang on a couple of different areas. So they developed a couple of methods to estimate the impacts of statistical mid-spatial frequency errors on shell ratio and MTF, but for idealized geometries that can result from, for example, diamond machining. They also did very thorough studies on the validity of that perturbation model that I mentioned before. This idea of I'm looking at the impacts of all these errors by adding them up in the exit pupil. They did a study in 2 dimensions and then in 3 dimensions of when does that actually apply? When can you actually do that and have it be accurate? And then a very recent paper by Liu and Herbert Gross on modeling of partially coherent light in systems that could have both statistical and deterministic structured surface areas. This was a very recent paper just over the summer. So I want to point those out. Now, when we talk about mid-spatial frequency errors, I'm talking mostly about where did they come, where do they come from and what do they do? I want to talk at least briefly about, well, how do I get rid of them? We generally don't want them. They're not a preferred feature in general of our systems. And there are ways to mitigate mid-spatials, but there are trade-offs. I can think about using a pseudo-random toolpath. So this is some work by Dunn and Walker shown here. Rather than doing a raster toolpath, doing a more pseudo-random meander, if you will, through the whole surface, so it disrupts the regularity of the error. Thinking about things like diamond machining here. So this is again the cusp-like errors I mentioned before. There's a fairly simple geometrical relationship between the radius of the diamond tool and the step over or feed per rev, or depending on which you're talking about here, that relates those quantities to the peak to valley of the amplitude of the structure. So I can increase the tool radius to lower my peak to valley, although that's going to place limits on how steep of a surface slope I can have in making my freeform or other surface. I can make the step over smaller, reduce this periodicity. But when I do that, I have to at least be aware that by reducing that feed per rev, it's going to take me longer to machine the part, which could exacerbate other errors. So for example, thermal drift that I mentioned earlier on. If you've already made the part and you say, well, can I reduce it? Can I reduce the amplitude? This can be done through post-processing techniques, although you've got to be careful can you reduce the mid-spatial without changing the underlying figure or form? There are a number of examples for this kind of work. Work with compliant polishing pads. So think of this as a polishing lap or pad that will, it has sort of long range structure, so it's not really going to change the form much, but it will, it'll adjust and sort of knock the tops off of the lower or the higher frequency structures here. An extension of this, so this is using conformal laps, but where they're vibrating during the motion. This is a process called Vibe that's used at Optimax. There's been some more recent work through the Center for Freeform Optics on using fiber bundles as this compliant polishing tool, and then even laser polishing, sort of scanning a laser to sort of locally smooth or melt the surface and get rid of the mid-spatials, but without changing the form. Okay. Now, all of these approaches, as you might guess, in general, are going to result in the process taking longer, additional time or additional cost. So it's an important question to say, well, how much? I know the mid-spatial's there. I don't want it, but can I stand? How much of it can I stand? Can I handle some? And to answer that, it really requires understanding of the connections between the surface errors themselves and the performance. So this opens up the question of what specifications, what metrics, peak to valley, RMS departure we talked about before, the RMS gradient or the slope of the surface, power spectral density, the structure function, which I won't really talk about in here, but it's another way of quantifying the error distributions on the surface, or something else entirely. Performance metrics like the Strehl ratio, the encircled energy radius. It's maybe if you think of it as a measure of spot size, MTF, or just aberrations like distortion or so on. So I want to think about this. I want to consider a simple case study, and so I'm going to assume I'm going to make the same nominal lens shown here with the same nominal surface statistics, but I'm going to get a different structure. So I've got, in this case here, I've got my cusp-like structure with a 40 micron period. And I've got this thermal cycle, this thermal drift error that I've alluded to before with a 1 millimeter periodicity. Now, if I look at doing this through diamond turning, I'm going to get this composite mid-spatial frequency error here shown like this. If I do a raster mill, I'm going to get this linear pattern here. But in both of these cases, if I were to look at the RMS surface error of this surface as a whole, it's the same, 82 nanometers. Now, if I start thinking about what'll this do, so I'm going to show, these are a couple of simulations. On the left here are going to be simulated results, so Rayleigh-Sommerfeld diffraction simulations in MATLAB, and then on the right, an image-based simulation that in this case was done in Zemax. So if I look at this particular system and I assume, hey, the lens is perfect, no errors, I get this nice sharp diffraction limited image. So this is of our student union here at UNC Charlotte. Now, if I now add this residual radially symmetric error on here, now my quantity, my performance has changed a little bit. I can quantitatively. So I end up with a Strehl ratio of about 0.8. My encircled energy radius is about 50 microns here. And then I've got a two-dimensional modulation transfer function that I'm showing. Now, let me go back up real quick just to kind of compare. So there's no error, and then there's with the radial error. So you can kind of see how the point spread function changes, how the MTF changes. Now, if I look at the same lens, but I do it through raster milling, now my point spread function changed quite a bit. I've clearly got these diffraction lobes right here. My two-dimensional modulation transfer function has got a lot more structure in it, but my Strehl ratio didn't change. My encircled energy radius didn't change, but my image changed quite a bit. Again, let me go back from turned, milled, turned, milled. So the takeaway from this is that standard metrics for specification and performance that in many cases are presented as single numbers or maybe one-dimensional representations, it might not do a good job of representing what's really going on. They might not distinguish between what I'll refer to as isotropic or anisotropic errors. For this case study we've been looking at here, a number of different comparisons. The RMSs were the same. Do the slope calculations, they're the same. The performance, the Strehls were the same. The encircled energy radius was the same. I've shown the linear structure function here. They're basically not meaningfully distinguishable. But again, we saw a difference in imaging performance and difference in modulation transfer, okay? So some other thoughts on this. The power spectral density representation that I showed before, it's typically shown as a one-dimensional representation. It's either a cross-section or an azimuthal average. When we think about standards, so I think about the ISO standards, there's a quote from this. Those texture standards are primarily intended for specification of polished optics, and basically you've got to be very careful, or care must be taken if you're using it with a material or a process that gives rise to a non-random surface texture, okay? Modulation transfer function is normally shown as a one-dimensional cross-section. We could think about doing two-dimensional MTF or two-dimensional PSD and so on, but they're a little more complex. How do we interpret them? How do we use them for specification? So to that end, just some work that's been done towards this area. Work done on extending the structured function to an area structured function or a two-quadrant area structured function. So this is work from Ling He and Chris Evans and Angela Davies. Some work on a two-dimensional aerial power spectral density, but plotted in a polar format, so for angular resolved errors. done by Perderman in Germany. And then where I'm going to spend most of my remaining time on, I'll say tools and metrics for surface specification and estimation for anisotropic errors. And this is work primarily by Hamidreza Ayarian at UNC Charlotte. Okay, so I'm going to focus and try to kind of wrap things up talking about this last part on these new methods that have been proposed for estimating performance, quantifying performance of more generalized errors. So not assuming isotropic or not necessarily assuming anisotropic, but can we come up with something that will apply to both? And the results of these are going to give results that are analogous to what I'll call the simple one-dimensional cases and metrics, but in such a way that they better represent the impacts of the anisotropic errors. So I'll talk about what we call the minimum modulation curve, what we call a polar RMS plot, and then this Q prime performance metric, which I'll define here in a minute. And I want to talk about these to kind of show the connections. So when we talk about modulation transfer function, I've already kind of alluded to this. There are situations where representation of the MTF is a one-dimensional cross-section, or maybe two orthogonal cross-sections, the tangential and sagittal plots, for example, might not be adequate. And this can apply to examples that I'm going to show here primarily with mid-spatial frequency errors, but it can apply to other structures as well. I could have an asymmetric on-axis impulse response, or just any system with an off-axis aberration. Okay, and I'll show an example of that in a minute. But the general idea here, this is showing for the two-dimensional MTFs for the two examples that we've been looking at here. And if I look at the cross sections here, so at 0 and 90 degrees, I've got the black is my diffraction limit. I've got this sort of small oscillation here, but those are both the tangential and the sagittal are the same, give me the same result with radial symmetry. But now in this case with the linear error, my cross section, this way I get this highly oscillatory modulation transfer function. But if I had to go vertically, it's essentially diffraction limited. Okay, so quite a bit of difference. Now ask the question, what happens at some arbitrary angle? And this can be relevant when we think about, I'm making a general imaging system, taking a picture of something. I may not know what the orientation of the image of the object I'm looking at is relative to my system. So it might be useful for a general performance specification. Could we identify a minimum modulation for a given spatial frequency independent of the orientation? Okay. So to this end, a fairly simple definition, what we refer to as the minimum modulation curve, or MMC. This is proposed as a tool to quantify these impacts. So the minimum modulation curve is basically saying, I look at my two-dimensional MTF, and I look at some radial distance rho, and I can look at what's the effective frequency at that distance rho from the center. And I'm going to, as a function of angle, capture the minimum value, okay? The minimum modulation as a function of angle at a fixed radius. Again, the radius corresponding to frequency. So in this particular case here with the linear raster pattern, I've got this oscillatory pattern. That's what we saw in cross section, but my minimum modulation curve is this red plot right here. So I'm basically saying that no matter which cross section I take, the modulation is not going to go below the red line. That's the fundamental idea. And again, that could be useful as a general performance specification. Now, just to show, this is not mid-spatial, but this is an example of off-axis performance for a Cook triplet. Similar idea, 20 degrees off-axis. I get sort of either tangential or sagittal MTF, but if I go at a particular angle here, I might get something which is considerably worse. So this red plot here is the minimum modulation curve for this Cook triplet. Again, but propose this as a metric for specification. Now, another method here of looking at surface data, what we refer to as a polar RMS plot, or PRP, was proposed as a way to quantify the surface errors on anisotropic surfaces. So the fundamental idea here is I might have a complex error map. I'm going to divide this data up into a series of columns, and I'm going to take the band limited RMS across each column individually. And then I'm going to, out of all those columns, I'm going to determine what's the maximum RMS value. Now, with that number, I'm going to then take my surface and rotate it by a small angle, repeat the process, find the maximum, rotate, and so on. And I'm going to associate and plot that maximum RMS value with a corresponding rotation angle, okay? So this example, there are two examples down here for just a simple sinusoid or linear or radial. In this particular case, the RMS deviation for both surfaces is 70 nanometers. When I plot my my data as described up here on my polar plot, the red line, the red circle is the data that I get from the radial pattern, and the blue is what I get from the linear pattern. And you'll notice that, particularly for the blue case, I get along the periodicity axis, I get this spike, okay? So that maximum value that I capture there, that the height of that spike, is what I'm going to refer to as PRP max. So for the radial pattern, it was 74 nanometers. For the linear pattern, in this case, it was 100 nanometers. And remember, I said that the overall, if I just said what's the RMS of the surface, it was 70 nanometers. So here's some more complex surfaces, looking at applying this tool as a way to quantify the surface. You know, some notable properties. You know, it's a way to plot band-limited RMS errors. You're getting information about the orientation of the errors, the width of the peaks correspond. You know, a wider peak corresponds to a lower spatial frequency. And then this is the takeaway. We propose that this PRP max value has a promise as a simple surface metric for connecting to performance. So this is explained here or quantified through this quantity, which we're calling Q prime. It's analogous to the Strehl ratio. Again, it's not Strehl ratio, but we're drawing analogies to it, leveraging some earlier work by Goodman on Fourier analysis for just the definition of the Strehl ratio, formally defined based off actually the OTF, the optical transfer function, but for small aberrations, the OTF and MTF are the same. So rather than Strehl looking at the ratio of the MTF, the area under the MTF to the area under the diffraction limited MTF for system, I'm going to do the area under the minimum modulation curve divided by the area of the diffraction limit. And then analogous to the work of Jungwirth and Stone that we talked about earlier for predicting performance, said we could predict, having information about refractive index and RMS surface error, we could predict Strehl ratio and MTF. We're drawing that analogy here as well, predicting, you know, our Q prime value and our minimum modulation curve value, but we're doing it using, rather than the RMS, band limit RMS error, we're using this PRP maximum value. So kind of showing how this actually works. This is for a radial and a linear pattern on a simple f5 PMA lens. Again, the RMS error of each is 70 nanometers, which predicts a Strehl ratio of about 0.84. If I apply this technique to the techniques that have been proposed to this particular surface, I get this maximum polar deviation of 74 nanometers, which gives me, again, approximately Q prime of about 0.84. And if I compare this blue dashed oscillating line, that's my minimum modulation curve, calculated from the rigorous, a rigorous calculation of the two-dimensional MTF. And the red line is basically the estimated prediction, just multiplying the diffraction limit by Q prime. And I can do, and so I get essentially the same performance for my radial symmetry as I did for the isotropic case. But for the linear case now, I predict a much lower performance, Q prime about 0.71, and same idea here. My minimum modulation curve is the blue dashed line. The red line is the prediction from this simple estimate. So again, it does a pretty good job of estimating, independent of orientation, what are the impacts on performance. Okay, kind of try to wrap things up here. I'll just say, again, I've shown a few methods for quantification and demonstrated a few methods for connecting surface specifications, optical performance, thinking about acceptance criteria, and so on. But I want to emphasize that there are opportunities for additional development and refinement of methods and standards, okay, for mid-spatial frequency errors. This is still an area of active work and active research. To that end, one comment I'll make is it's actually a new Center for Freeform Optics project that we've initiated for further advancing the ideas of design and tolerancing of imaging systems for mid-spatial frequency errors. We've talked about the importance of specification and acceptance criteria. We need clear connections between the surface and the performance. What's also needed, though, is understanding and availability of modeling capabilities and procedures. How do you, if I have data, what do I do with it? How do I actually model and design and tolerance a system? So we're working on expanding all these areas on, the metrics and criteria, developing capabilities and procedures in commercial software packages, and then also creating a mid-spatial frequency data library. So a number of different examples, case studies with lots of very detailed surface error data, but also metrics and so on, as sort of a reference, as a source for teaching and training and education, okay, as well as design. So if you're interested in this, please feel free to reach out if you've got any questions. So with that, I want to go ahead and try to wrap things up. I do want a number of acknowledgments. Again, I really want to thank the National Science Foundation for their support of CIFO through the IUCRC program. I really want to thank the center itself and the other the other directors within the center, and particularly I want to thank the CIFO Industrial Advisory Board for their support and continued guidance and involvement in this project. I want to thank a lot of the work that I've shown here, most if not all. This work, this isn't necessarily stuff I did. This is students and otherwise. So I really want to thank Reza Arian and Jason Schultz and Zara Hosina Makaram, so former students of mine, and Dr. Angela Davies Allen at UNC Charlotte, and then my current student Luke DeMars, who made major contributions to this work, and then partners on sort of previous and existing MSF programs through CIFO. Okay. So I also want to draw attention to, there is a feature issue on freeform optics in Optics Express. Actually, the submissions are still open for till the middle of September. I'd like to encourage all of you to consider a submission, whether you're interested in mid-spatial frequencies or just more generally areas of freeform with design or manufacturing or applications. So with that, I'm going to go ahead and finish. And thanks for your attention, and I'd be happy to try to take any questions.
Yeah, thank you so much, Tom. That was great. As Tom said, we've got a couple minutes. We've got about 7 minutes to take some questions. So feel free to type them into the chat and comments as well. I'll make sure Tom sees them. So my first question for you is, what instrumentation would be needed to measure the proposed metrics for specification of the mid-spatial frequency variation?
What would be used to measure? So I guess I'm interpreting that from sort of measuring of the surfaces themselves. I'll interpret it that way. If I'm wrong, somebody can correct me.
Yeah, if you want to type, whoever typed that question, if you want to type a follow-up, feel free.
Just thinking about, how do you, or more generally, how do you measure a mid-spatial? That could be probably its own presentation and discussion. More generally, I mean, I think the answer is the answer is going to be, it depends on what types of errors might be present. Are the errors nominally uniformly distributed or isotropic, or are they anisotropic, more structured? So contact profilometry is a normal way to do this. Very high vertical resolution in particular. Although there might be challenges, if you're measuring a structured surface or a complex two-dimensional error, that a contact one-dimensional trace might not give you what you need. There's been a lot of work done in using deflectometry, sort of projection of fringes on the surface, and then image recognition and pattern recognition for two-dimensional measurements of mid-spatial frequency errors. Very quick, very powerful technique, although depending on spatial frequency content in the pattern, maybe there's some challenges. More generally, interferometry will tend to be a good way to go for high resolution, vertical and lateral. Although depending on the size of the component or area you're trying to measure, there might be a necessity to measure, maybe measure a small area using, for example, like scanning white light interferometry with a higher NA numerical aperture objective. But then, so you get high resolution over a small area. But then if you want to measure a big area, you might be able to do stitching of multiple pictures, but then that introduces its own set of challenges. So I'm not sure if that answered the question, but it definitely some ways, some general approaches for gathering the data, and then it could be used as the basis for the calculations.
And just to clarify, that person says, yeah, that's correct. They're talking about the surface.
Good, okay.
So you've already mentioned some of these. What are the challenges of measurement of MSF surface errors?
Yeah, I guess I probably hit on a couple of those already. Depending on the complexity and the range, when I say complexity, I mean, is it the same pattern kind of everywhere, or highly structured, or sort of in between? Some of the things that I showed were fairly involved two-dimensional, distributions of errors from different sources. And then different ranges, potentially, even within the quote-unquote mid-spatial regime, what's the range of spatial frequency content might drive towards one method or another. Again, the contact profilometry traces could be good, but if it's a complex two-dimensional signature, going deflectometry for 2 dimensions, but and fairly quick, and then interferometry, start thinking about high resolution, but again, you can end up being an extremely large amount of data, which just stitching the data together from the different fields can be that can be a numerical beast by itself. Not to mention then what do you do with the data for the calculations for performance? So,
all right, thank you. I'm going to ask you one more for now, but everyone feel free to type in more questions. We'll answer you later. So what methods are used to model the effects of MSF errors on optical performance?
Okay, good question. Yeah, again, and I guess good question with a long answer. Yeah, and again, it depends. There are capabilities in commercial software packages, several commercial packages, for doing some of the types of analyses and things that I've shown in here. But there can be limits, or we've seen, or we've run into some limits, maybe in terms of the computational requirements, the assumptions made, maybe in particularly more the physical optics models that are used, or just trying to represent the data. We found it necessary to maybe sometimes create custom, macros and DLLs and so on within certain packages to describe the kinds of surfaces. But generally speaking, ray tracing may not be sufficient. Because we're talking more because of the spatial frequencies that are involved. It's more diffraction, interference type, or just wave-based properties that we've got to worry about. We'd like to use full wave-based, either scalar or vector theory, and hopefully not vector needed for mid-spatials, but these can get quite computationally intensive. There are some in-betweens with what I kind of call pseudo ray tracing, like dressed rays or Gaussian beam decomposition can be used. So there's things like in Code 5, what they call BSP, or beam synthesis propagation, is a technique like this, or in a program called Virtual Lab, they have what they call field tracing. These are applicable. Bottom line, we use all of these packages, and we also, in many cases, have said, well, we can't find what we want in a commercial package, so we write it ourselves in MATLAB. So, long answer to a short question.
Appreciate it. And thank you everyone for your questions. If you think of another one, you can reach out to us at webinar@photonics.com, which is webinar@photonics.com. And you can download the paper, again, Freeform Optics for Imaging, published by OSA this year. Right in the chat, there's a direct link for you, or you can type in your search engine, Optica Freeform. And again, this whole session was recorded, so you will be able to access it online within a few days. You're going to get links in your email inbox. You won't have to go hunting for it. And one more time, I'd like to thank our presenter, Dr. Tom Selesky, Professor of Physics and Optical Science and Site Director of CIFO at UNC Charlotte. And thank you everybody here for participating in the Freeform Optics webinar series. This has been Mid-Spatial Frequency Errors. Thank you so much, everyone.
Thanks, everybody.